Hello everyone, I hope you are doing well. So in today's video, we are going to go through the 2021 physics exam short answer questions where we'll pretty much be continuing off from questions 10 to 20. And so like always guys, before I start this video, if you guys want a private tutor in specialist methods, physics or chemistry, you can always email us in the, through this email pretty much. And yeah guys, let's smash through this video. Question 10. A new spaceship that can travel at 0.7 C has been constructed on Earth. A technician is observing the spaceship traveling past in space at 0.7 C, as shown in figure 10. The technician notices that the length of the spaceship does not match the measurement taken when the spaceship was stationary in a laboratory. Beautiful. So we know when the spaceship was stationary in a laboratory, because it was stationary in that laboratory, it is our proper length. So when it's traveling pretty much at the speed of light, and when the technician is seeing, he's going to be seeing length contraction. He's going to so beautiful. And that's why it's not basically, it doesn't match the measurements that was in the laboratory. All right, but its width matches the measurement taken in the laboratory. Beautiful. Of course, let's understand why the width doesn't change. It's because remember, only length contraction only occurs in the direction of motion. For example, can you see how this is going to the right? And can you see how length is parallel to the direction of motion, which is going to the right? Whereas if you look at your width, it's actually perpendicular to the direction of motion and hence doesn't get affected. Remember, length contraction only happens in the direction of motion, which is our length in this case. So basically this here will be contracted when it's traveling basically. Whereas this one will stay the same. Beautiful. Explain in terms of special relativity why the technician notices that there are different measurements. Of course, because one's gone through length contraction for the length of the spaceship, but not for the width of the spaceship. And basically, you just want to talk about how length contraction only happens in the direction of motion. And yeah, so your width would not be affected. So let's write what we basically said. Let's use this color. So I'm just going to put 2 dot points basically. Technician. So technician is measuring length contraction basically. So that's why he's seeing it not matching. So the technician is measuring the length contraction. And we said that length contraction only occurs in the direction of motion. In the direction of motion. Beautiful. Yeah. So did we answer the question? Special technician notices, yep. Technician measuring length contraction only occurs in direction of motion. Beautiful. B. If the technician measures the spaceship to be 135 meters long while traveling at a constant 0.7 C, so that's your basically length contracted because it's traveling at that speed. What was the length of the spaceship when it was stationary on Earth? So what we're trying to basically calculate is the proper length. So we know that length contracted is basically your proper length over your gamma, which is your Lorentz factor. And so to calculate our proper length, it's just your dilated length. Oh no, what am I dilated? Your contracted length times your gamma. And so your Lorentz factor can be calculated from this formula, 1 over square root of, so 1 minus the speed that it's traveling, so 0.7, so 0.7 C, so 0.7 times C, which is speed of light, squared, and speed of light squared itself. So we just see squared itself. So that's going to give me my Lorentz factor. So that's going to be 1 over square root 1 minus 0.7 times 3.08 times to the power of squared 3.0 times 10 to the power 8 squared. So that gives me basically 1.4. So your proper length is your contracted length, which is 135, times your Lorentz factor. So that's going to be giving me basically 189. That's basically your proper length. Beautiful. Question 11. Figure 11 shows a system of two ideal polarizing filters, F1 and F2, in a path of an initially unpolarized light beam. The polarizing axis of the first filter, F1, is parallel to the y-axis, and the polarizing axis of the second filter is parallel to the x-axis. You don't even have to stress about this. Those students who are pretty much doing the 2024 study design and greater, especially in that new study design, this is not anymore in the study design. This is polarization. So you guys are lucky, so you don't need to watch this, basically. Skip this question. But I'm going to still explain it, just because it's good to kind of, I want to try to finish this whole paper. So yeah. Alright, so basically, will any light be observed at point P? Alright, let's think about it. So we have the X and Y, and so let's just basically draw a wave that's only in the direction of the Y and X. So this here, this is basically in the Y direction. Imagine this here is your Y direction. As you can see, it's like Y. And then we're also going to draw like an X one. We basically want to draw red. That's parallel basically to the X value here. That. So I'm going to just kind of this. And this here is going to be like that. Perfect. So it's like a 3D model. And so what's going to happen is this wave's going to basically pass through. It's going to go like, inside, blah, blah, blah. And then it hits this polarizing filter. Basically what the polarizing filter is, it's going to block all the other, light. It will only allow the one that's parallel to the y-axis. So basically only the orange, because that's basically the light that's in the electromagnetic light that's basically parallel to the y-axis. So it's going to block the red part. So imagine just basically allows this. If I draw that nicely here, like that, it basically just allows that light here. Now, all right, beautiful, something like that. There we go. So it's only allowing this light. So it's blocked that light, and now it's passed through here. But the problem is, have a look at this. When it comes to your filter 2, this here is only parallel to the x-axis, but there's nothing we have. This is the wave that's coming. It's only going to be basically in the in the y direction. So it's going to also get blocked. So when this gets blocked, basically the person at point P is not going to see any light basically coming, and because everything's basically blocked. So will any light be observed at point P? Absolutely no. So we're going to say no light will be observed. So we're going to a little bit have to explain, because how many marks on it? 2 marks, 2 marks. Okay. So yeah, just basically explain like what's going to happen at F1 and then F2. So we're just going to kind of write. So at F1, your filter 1 allows only polarized light that is parallel. So parallel to the y-axis. Hence, the others cut off, basically. Done. F2 allows only polarized to y-axis. This light, so we can say this light is stopped and does not pass, basically, and does not pass. Does not pass through. And that is it. Beautiful. All right, that's nice. 2 marks should give you those 2 marks. Question 12. Let's try this. A physics teacher is conducting a demonstration involving the transmission of light within an optical fiber. The optical fiber consists of an inner transparent core with a refractive index of that, and an outer transparent cladding with a refractive index of this, and single monochromatic light ray is incident on the optical fiber as shown in figure 12. You don't even have to know this. This is out of the study design. So the new study design, you don't have to know about refraction, and all these stuff here. So you guys are lucky. So you don't have to basically watch this part here. All right, let's have a try at this. So determine the angle of incidence, theta, at the air core boundary show working out. All right, so we want this angle. Okay, so what do we have? So we know that the refractive index of air basically is, I'm going to call N1, is 1. We knew that the refractive index of air is that. We also know that the refractive index of the inside, your refracted angle, that's, to normal, is going to be 32 degrees. Because if this is 32, this must be 32. You can do basic trigonometry to basically prove that. If this is 90 degrees here, that's 32. Then this here must be, so what's 180 minus 90 plus 32? This here angle must be 58. So that's 58, basically. Because this is 90 degrees, what's 90 minus 58? That gives me 32. Yep, so we have basically just proved that this point here, this angle here, must be also 32. Done. And we also have the refractive index for that. So we can actually use our formula. N1 sine theta is equal to N2 sine theta. N1's, 1. Sine theta is what we're trying to calculate. N2 is the N core one, so 1.46. Sine your angle that's refracted, which is basically 32. So your theta is basically your sine inverse. 1.46 sine 32. That's going to give me 1.46 sine 32. Basically, to how many degrees? Significance, we'll do 3. So, so 50.7 degrees. Will any of the initial light ray be transmitted into the cladding? Explain your answer and show any supporting working. All right, so what's happening is basically, okay, we have this light ray coming here. Is it so let me actually draw a normal here. Let me draw a nice normal line here. Just kind of show this. So let me draw a normal line. So when this light ray comes here, is it going to basically pass? Is it going to refract into the cladding? Or is it going to be totally internally reflected going back to the core? So that's what we kind of want to determine. And to know what really happens is we have to look at the angle of incidence. So let's have a look at the angle of incidence. So your angle of incidence, of course, is this angle here. It's between the normal and the thing. So what's this basically? This has to be 50, what is it? So remember, this is a 90 degree angle here. That's a 90 degree angle. So what's 90 minus 32? It's going to be basically that. 90 minus 32. This here angle is 58. So your angle of incidence is 58. What we can do is we can determine the critical angle. Because what the critical angle tells us, it's the angle that tells us where basically it's between the boundary of the cladding and the end core. And if our angle of incidence is greater than the critical angle, it has been totally internally refracted. But if it's less, then it's basically refracted through the cladding. And that's what our conditions are. That's what you basically, I think, need to just kind of prove. So what we need to basically do is state these two stuff. If your angle of incidence, is greater than your critical angle, total internal refraction happens. Total internal reflection happens. If your angle of incidence is less than your critical angle, then refracted into cladding. Let's check what's happening. So we know our critical, your angle of incidence is what? 58. Let's calculate our critical angle. So remember, critical angle is basically N1 sine theta C is equal to N2. That's the formula. So what's N1? So we're basically going from N core, so that's going to be 1.46 sine theta C, N2, which is 1.42. So your theta C is the sine inverse of 1.42 over 1.46. And that's going to give me what? 1.42, 1.46. That gives me around 77 degrees, basically. 77 degrees. So now we've got that. Let's see what condition has met. We can see that your angle of incidence, so your angle of incidence is less than your critical angle. Hence, it is going to be refracted into the cladding. So basically transmitted, let's say transmitted, because that's what they're saying. So hence, transmitted into the cladding. Beautiful. Question 13. In Young double slits experiment, the distance between two slits, S1 and S2, is that the slits are 1 meter apart from a screen on which an interference pattern is observed. Beautiful, as shown in figure 13a. Figure 13b shows the central maximum of the observed interference pattern. Alright. If a laser with a wavelength of this is used to illuminate on the two slits, what would be the distance between the two successive dark bands? So we just want to find out change in x, basically. So we know that change in x is basically wavelength, your length between the your slits and the your your screen, and then distance between the slits. So what's your wavelength? We said it was 620 times 10 to the negative 9. Make sure it's in meters. Your length between the slits and the screen is 1 meter, and your distance between those two slits are 2 millimeters. So make sure times 10 to the negative 3 to make it into meters. 620 times 10 to the negative 9, 2 times 10 to the negative 3. And we want it in millimeters, so times 10 to the power 3. We get basically 0.31. I just want to double check if I've made any mistakes. Looks all good. Just let's double check. So 620 times 10 to the negative 9, 2 times 10 to the negative 3, and so times 10 to the power 3. Beautiful. That looks all good. Explain how this experiment supports the wave model of I. Beautiful. What an easy question. Now you should know, to kind of explain what's happening here is, all you need to explain is this. This here is an interference pattern. And so interference is basically a wave phenomenon, basically. That's it. But you need a little bit more detailed. So how? All you want to say is basically be like, this, experiment proves that there's places where there are, bright bands and dark bands, which proves that there are constructive and destructive interference patterns. Because the experiment proves that there's an interference pattern, and interference pattern is a wave phenomena, this hence supports the wave model. Just this kind of beautiful answer you put. It's one of the most kind of repeated questions in past exams, so it's like one of the most easiest to get full marks. So I think that's what you need, especially it's 2 marks, yeah. So I'm going to write down, and yeah. So let's write that down. So the experiment proves interference from the constructive, so from constructive and destructive, so destructive interference pattern, interference patterns. This is a wave phenomena. Wave phenomena, and hence supports the wave model. Beautiful. Done. Next question. Oh, just right now looking at this question, this gives PTSD. So this question here, I remember doing it when it came out, when this paper came out, and believe me, I did it right, but I was disgusted because I think I'll explain why it's one of the worst questions I think that, they've put in an exam for a long time. And I'll explain it as we go through it. A distant fire truck traveling at 20 meters per second to a fire has its sirens emitting a sound of constant frequency of 500 hertz. Chris is standing on the edge of the road. Assume that the fire truck is traveling directly towards him as it approaches him and directly away from him as it goes past. The arrangement is shown in figure 14. On the diagram below, sketch the frequency that Chris will hear as the truck moves towards him and moves away from him. The 500 siren signal is shown as a dotted line for reference. No calculations required. Okay, so when I was doing this question, I basically, because I did university maths, I knew how to do this question basically, but I think it went above and beyond the V-class study design. When they put this question, I was like, how are students going to know how to do this? Because it is very hard. So I will explain how to do it. But like, guess what? You guys don't have to now do it because it's not in the study design. Doppler's effect is out. You don't even have to do this question, so skip it. But I'm just going to basically show how I did it when I was doing the exam, and I knew that a lot of students wouldn't know how to do it. It's quite hard, I'm not going to lie, the way they put a question that was like, I think I had it in my university test if I wasn't mistaken for my physics 1. So to put a question like this was disgusting, especially for a high school year 12, especially the textbooks didn't kind of go more detail on Doppler's effect. Like the Heinemann book didn't go in as much detail. So a lot of students only knew the basics, but this is too much deep. And it's like, this is too much deep. And so, yeah, absolutely stupid question. So, so we need to kind of draw how it's going to happen. So basically, the formula that I was using is basically my Doppler's effect formula, where the frequency of an observer is equal to basically your frequency, your velocity of your sound, the speed of sound basically, which is basically, let's write it down, which is, let's say in this case 340, plus your speed of your detector, which is 0. It's the person's basically the one that's kind of measuring it. It's just standing straight. So we can just say 340 basically, over your speed of sound plus your velocity of the source. Now, it depends on the velocity of the source. If it's approaching you, it's going to be negative 20 meters per second, basically. Because it's basically, your denominator is going to get smaller and your frequency that's going to be observed is going to be high. Yep. Or multiplied by the frequency, your frequency of your source, which is 500, constant 500. So this value here, basically, it just tells you that as the frequency that will be observed by the person, basically, it's going to be constant. It's going to be more than 500. Like if you put this, it's going to be, I don't know, like maybe 700. I mean, let's do it by calculator. So 340 minus 20 times 500. So basically 531. So it's, of course, it's more than 500. But basically, it's a constant frequency as it passes towards Chris. So it's going to be like this, going towards Chris, like that's where Chris is. And so, you mean there's no observed frequency that's going to be here, but as it moves past him, now we can put a plus here, because it's moving past. So now that's going to have, what's going to happen here, it's going to be 340 plus 20 times 500. So that's going to be 472. Basically, it's going to go like this, a constant frequency as it goes away from Chris. All right, I mean, look, I'm not going to go in very detail about this question. I was quite disrupted when I was doing it because I was just, I felt bad for many of the students because I think they just weren't fair by putting this question in an exam. So, and you guess what? You guys don't even need to learn it, especially in a new study design. This is not anymore in the study design. So you guys can take care, enjoy yourselves. Skip this question, absolutely. Name the physics principles involved in Chris's experience. Basically, yeah, Doppler's effect. Doppler effect. Beautiful. Question 15. Let's have a try at this. A photoelectrical experiment is carried out by students. They measure the threshold frequency of light required for the photo emission to be this, and the work function to be this. Using the student's measurement, what value would they calculate for the Planck's constant? Outline your reasoning and show all your working out. Give your answer in joules per second. What a beautiful question. Now, if you have the threshold frequency and the work function, and you're basically told to calculate Planck's constant, this just reminds me of the kinetic energy max versus frequency table graph. So let's just draw a graph for that. So basically, you're going to have like a graph like this. Of course, this is your kinetic energy max, so Ke max. And this is your frequency in basically hertz, and make sure this is in joules. And so if I have my threshold frequency, which basically occurs at the x-axis, so here is what? It's this much, so let's write that down. So it's going to be in terms of, coordinates, it's going to be 6.5 times 10 to the power 14, 0. And your work function, which is your y-coordinate, which occurs, at the bottom, which is, let's say it's here. And so it's basically just a straight line that passes through these two. And the gradient of this straight line is your Planck's constant. Now, this point coordinate here has to be basically 0, comma, negative. Make sure you put a negative because it's below. Negative 3.2 times 10 to the power of negative 19 joules. Beautiful. And so now, let's calculate the, if we have two coordinates, we can easily calculate the gradient of this graph. Oops. Let me just, right there. All right. So, your gradient is going to be your, this is 0 minus 3.2 times 10 to the negative 19, all being divided by 6.5 times 10 to the power of 14 minus 0, basically. And this is your Planck, your m, your gradient is your Planck's constant, basically, which is 3.2 times 10 to the negative 19 and 6.5 times 10 to the power 14. So that gives me, basically, let me write it here, 4.9 times 10 to the power of negative 34. Beautiful. Question 16. Light can be described by a wave model and also by a particle model. The rapid emission of photoelectrons at very low intensity supports one of these models but not the other. Identify the model that is supported and give a reason for your answer. Model support. Okay, this is very easy. The model that's supported in this is basically the particle model. Why? Because, think about it. Why is having, low intensity, why are still photoelectrons basically being emitted? Now, you should already know that intensity is, proportional. Let me write this. So basically, intensity in the particle model, so intensity is basically proportional to the number of photons emitted. So intensity is not energy. So having a high intensity doesn't mean the photons have high energy. It just means the number of photons are greater. So we also know by the particle model that basically one photon is only observed by one electron. So let's think about it. If we have a photon here, let's say we have low intensity. Let's say we have a low intensity. It means that we have a little number of photons basically being emitted, only little. And so basically these photons have energy. Now this energy, remember, energy is independent. It's independent on intensity. It doesn't get affected. So let's say this is your photon, and basically it has energy. And this energy is very, very high. It's higher than the threshold frequency. This energy, it's basically higher than the work function. And say we have an electron here. Even though there are limited, if intensity is low, it means that there's less number of photons being emitted. We only need one basic photon to be absorbed by one electron to be emitted, because remember, one photon gets only absorbed by one electron. And so if this, energy, if this photon basically gets absorbed by this electron and it's greater than the work function, this electron is basically going to be emitted. And so we have basically photoelectrons being emitted. Get that? So overall, one of the most important things is just to realize that your intensity is not energy. That's what the wave model predicts. So the wave model predicts basically that intensity is the amplitude of the wave. Having high intensity means having more energy. You're giving more energy. And so that's wrong. So absolutely, that's how I would basically explain it. So hope that makes sense. So that's what we just talked about right now. So this model support is the particle model. And we're just going to need to justify our answer. So I'm going to be I'm going to try to detail this so you guys can understand. All right. In particle model, So in the particle model, the intensity of light is proportional to the number of photons emitted. Since we know, since one photon is absorbed by one electron, low intensity light still produces a photoelectron, as reducing intensity of light only affects the number of photons and not their energies. Beautiful. That is nice and detailed. For 2 marks, yeah, that should get you. Question 17, let's have a try this. A space sail mounted on a tiny interstellar cylindrical probe relies on momentum of photons from a nearby star to exert a propulsive force as shown in figure 13. So what I believe is like basically these are photons and they're basically hitting this, it's like a little paper, I'd say, and basically getting repelled. The photons struck the sail at 90 degrees to the surface and reflect elastically. Beautiful. They said elastically. Remember, elastic collisions basically are where the kinetic energy is not lost. Basically means that what's happening is basically when they're being collided and they're going to be kind of propelled, their velocity that they started with is going to be the same velocity that they're going to be going in the opposite direction, because there's actually no energy lost, no kinetic energy lost. That's what they mean by elastic. Yeah. Scientists need to calculate the force exerted by the photons, which have a frequency of this, show that the momentum of the 7 times 10 to the negative 15 photons is equal to that. So we want the momentum. Let's look at a formula for momentum. So we have the frequency and we want to find the momentum of these photons. All right. So frequency. Beautiful. So I know that momentum, just looking at my formula sheet, hf over c. So I can use this formula, which means that to get my momentum, what's my h? Look at my formula sheet. That's 6.63 times 10 to the power of negative 34. Your frequency is 7.0 times 10 to the power of 15, all divided by your speed of light, which is 3.0 times 10 to the power 8. That's going to give me that value. 0.63 times 10 to the negative 34 times 7.15, 3.0 times to the power 8. And that gives me, yes, it looks the same. Beautiful. Basically 1.5, if I'm going to use the same, 5 times 10 to the power of negative 26 kilograms meters per second. Done. 2.0 times 10 to the power 18 photons of this frequency strike the space sail every second. Calculate the force that the reflecting photons exert on the space sail. Show you working out. Give your answer correct to decimal place. Because we've basically touched bases on momentum, we should basically think that we're going to use momentum to calculate the force. So let's think. Now, the only formula that comes to my mind using momentum, and we have time also every second basically, is impulse is equal to your force times your change in time. Because your impulse is your change in momentum, and we have our momentum, so we can work with that. We can calculate this force basically. That's going to be our force, and we know the time every second. So all right, that's what I'm thinking. So let's calculate our change in momentum with your impulse. So your impulse is your mass, v minus u, your change in velocity. Now let's think about this. Basically, when these photons, let's take this as positive, basically. Let's take right as positive. So basically, these photons are traveling at a velocity. Let's call it u, your initial velocity. And so when they basically, reflected, because they're elastically, basically that velocity, that u, is going to be the same. It's going to be, you know, your velocity, your final velocity, it's going to be the same as u, but in the opposite direction, because the speed is the same. You know, the speed hasn't changed because it's an elastic collision. So we can actually rewrite this as v, basically. I want to write that as v. So your basic initial velocity and then your after velocities are going to be the same. So putting this in this formula, but make sure the directions are different. So we can say your impulse, your final velocity is negative v, because it's in the opposite direction. It's going not to the right, but this way. And your original is minus v. So overall, that gives me m negative 2v, which is basically negative 2 mv. Now, this negative 2, why do we have a negative? It just means we're going the opposite direction. Your impulse is basically in the opposite direction. Now, we don't need that, to be honest. We don't worry about that negative because we're not trying to calculate the direction of the force or anything like that. So we can leave it like that. And so your impulse is basically just 2mv. mv is basically momentum, as we know. So basically, it's the same as 2p, which is your momentum. And so your impulse, let's calculate your impulse. Your impulse is what? It's 2 times our momentum, which we calculate, which was 1.5. 5 times 10 to the power of negative 26. Now, this will calculate the momentum of only one photon. Now, remember, we have this much photons being emitted every second, so we just need to multiply this by this, because that's how many photons are being emitted. So 2.0 times 10 to the power of 18. Okay, beautiful. So that's going to give you my overall impulse of those photons. So let's do that. So 2 times 1.55 times 10 to the negative 26 times that, we get basically 6.2 times 10 to the power of, so 1, 2, 3, 4, 5, 6, 7, 8. Negative 8 kilograms meters per second. And so putting that in our formula, so your force, basically your force is just your impulse, so 6.2 times 10 to the negative 8, all divided by your time. And basically your time is every second, so basically it's the same thing. It's that 6.2 times 10 to the power of negative 8 newtons. That looks perfect. Absolutely done. All right, question 18. Let's have a try this. Scientists are conducting experiments to compare the circular diffraction pattern formed by X-ray photons and electrons when they pass through a small circular aperture. The X-rays photons have an energy of 100 electron volts and pass through an aperture of diameter of this. So we're given the diameter and the energy of X-rays, and the electrons are moving at the speed. Show that the Rogoli wavelength of the electrons is equal to that. Easy. So we're given the velocity, so we can find the momentum basically, which is your mass times your velocity. All right, so your mass of electrons are 9.1 times 10 to the negative 31 times your velocity at which they're traveling, 5.0 times 10 to the power of 5. So that's going to be 9.1 times 10 to the negative 31, 5.0 times 10 to the power of 5. So that's overall 4.55 times 10 to the negative 25. And so we know that to calculate the wavelength, your de Broglie wavelength, it's your h over your momentum. So that's going to be, so what's your h, 6.63 times 10 to the negative 34, all being divided by that momentum. Or times 10 to the power of negative 25. So that gives me 6.63 times 10 to the negative 34 divided by that 4.55 times 10 to the negative 25. All right, did I do everything right? Yep, looks good. So basically I get the same thing as that. Wait for 1 point, let me write it. So 1.56 times 10 to the negative 9 meters basically. Beautiful. B. The scientists want an aperture of 4 the electrons that form forms the diffraction patterns with the same spacing as the diffraction patterns formed by X-ray. So we want the same basic spacing, so the same diffraction pattern. Calculate the diameter of the aperture that the scientists should choose. So we're working out. So for the electrons, so we want to form basically the same diffraction pattern. Now we know that diffraction, so let's think about this. So we know that diffraction is what? It's your wavelength over your width. So if I want the same diffraction pattern, I want the diffraction pattern, sorry, let me write that down. So I'm going to write your diffraction, remember your diffraction, so which is, your wavelength over your width for basically the electron. Let's write E in these two. So your wavelength of the electron and the width of the electron should be equal to your diffraction of the X-ray. So X and your wavelength of the X-ray. If we want these, remember this is your diffraction of your X-ray and this is your diffraction pattern of your, basically these are spacings in the diffraction pattern of the electrons. If we want them to basically have the same spacing, we want them to be equal. And so we have the, wavelength of electrons, basically, and we want to calculate that, the width of the aperture of electrons. We have that one, so the width or the aperture of the diameter, 1.24 micrometers of the X-ray, and we just want the wavelength of X-ray. Let's calculate that. So we're given the energy, so that's beautiful. So basically, let's have a look at this formula sheet. So we know that wavelength wavelength is hc over your energy of a photon, which is h is going to be what? So h is going to be 4.14 times 10 to the power of negative 15 over times c, sorry, so times 3.0 times 10 to the power of 8, and the energy, which is 100. So that's going to give me my wavelength of my X-rays. All right. So 4.14 times 10 to the negative 15 times 3.0 times 10 to the power 8. Divided by 100. So that gives me, wow, so it's a very small number, but it gives you 1.242 times 10 to the power of, so 1, 2, 3, 4, 5, 6, 7, 8. Negative 8 meters. I just want to double check it. So 1, 2, 3, 4, 5, 6, 7, 8. Beautiful, 8 meters. And so now I can put this all in my formula here and try to calculate this here. So, all right, so I'm going to use a different color. Let's use red. So the wavelength of the electrons, which are 1.46. So 1.46 times 10 to the power of negative 9, all being divided by your width of the electron. That's what we're trying to calculate. Your wavelength of your X-rays, which are 1.242 times 10 to the power of negative 8, all being divided by your width of your, which is 1.24, so 1.24 micro, so times 10 to the negative 6 to change it to meters. So basically, I'm going to calculate that first. Let me rewrite that. So 1.46 times 10 to the negative 9, sorry, all divided by your width of the electron. So that gives me what? That gives me 1.24 times 10 to the negative 6. Gives me basically 0.0016. Hence your width is basically 1.46 times 10 to the negative 9, all being divided by that number. Beautiful. So 1.46 times 10 to the negative 9, like that. So I get my answer now. So let's see what it is. So it's basically, let me just write it here. It's 1.5. So yep, so 1, 2, 3, 4, 5, 6, 7 times 10 to the power of negative 7. It's basically 1.4576, but I've just kind of rounded up to 1.5. Beautiful. That looks perfect. A very long question for 4 marks. Beautiful. You need to think of kind of out of the box using this here ratio, but yeah, it makes sense. All right. Question 19. A simplified diagram of some of the energy levels of an atom is shown in figure 16. All right. Identify the transition of the energy level diagram in figure 16 that will result in the emission of a 565 nanometer photon. Show you working out. Beautiful. So the energy that will be released by this photon is hc via wavelength. Now we know a wavelength, so we know h is what? So we want it in terms of electrovolts. So we're going to use 4.14 times 10 to the power of negative 15. I want to just double check that. Yep. Your speed of light times 10 to the power 8, all divided by your wavelength, which is 565 times 10 to the negative 9 nanometers. So that's going to be 4.14 times 10 to the negative 15, 3.08 times 10 to the power 8, 565 times 10 to the negative 9. And so that gives you basically approximately 2.2 electrovolts that will be emitted basically from emission. So let's think about it. It's not going to be this one, 4.9 minus 0, nope. Is it going to be this one, 6.7 minus, so 6.7 minus 4.9? Nope, that's going to basically release a 1.8 electrovolts. What about this one here? 8.9 minus 6.7. Yes, that's 2.2 electrovolts. So basically going from here to here, that will release that 2.2 electrovolts of energy for a photon. Beautiful. Question B. A sample of the atom is excited into the 9.8 electrovolts, so basically it's here, and a line spectrum is observed as the states decay. Assume that all possible transitions occur. What is the total number of lines in the spectrum? Explain your answer. You may use the diagram to below to support your answer. All right, 2 marks. Okay, so they're talking about, like, in terms of the spectrum, they're talking about the emission spectrum. Now, basically for an emission spectrum, what it's going to emit, basically, when it has those lines, these lines tell you the wavelengths that are being emitted, basically, if that's nice. Yep. So let's first calculate all the energies that are going to be emitted when the, electrons basically, what are the possible photon energies that are going to be emitted. So if it's, at 9.8, this energy can be emitted, basically. Let me write that down nicely. This one can be emitted. Also, this one can be emitted. This one can also be emitted. This one here can be emitted. This one over here can be emitted. So this one here can be emitted too. This one here too. What else? So this one also here. This one here. And this one over here, basically. So these are all the possible, if I haven't made a mistake, yeah, these are all the possible ones. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes, so 10 emissions that we can basically, get for possibilities when it's excited at 9.8 electrovolts. Now, let's write those down, basically. Let's double check. So the first one's going to be basically, so this one over here is going to be emitting a 9.8 electrovolt energy. The other one is basically 9.8, so 9.8 minus 4.9. So that's going to emit a 4.9 electrovolt. So that's going to be done. The next one is going to be 9.8 minus 6.7. There's going to be 3.1. The next one is basically 9.8 minus 8.9. Sorry. 9.8 minus 8.9. 0.9. So, alright, 0.9 electrovolt. I think they should put more marks for this because I think you just need to be careful. Don't say 10 here. That's wrong. You need to just be careful. You want to check all those, the energies that are absorbing. So if we have some energies that are the same, that's going to basically make this different. And I'm going to explain how. Let's just observe. The next one is basically 8.9 so basically it's just 8.9. So 8.9 electrovolts. That one there. So 8.9 minus 4.9. 4 electrovolts. Oops. So 4 electrovolts. There we go. 8.9 minus 6.7. 2.2 electrovolts. 6.7. Where's the next one? 6.7 that we can release. And that's going to be that one. And 6.7 minus 4.9. 1.8 basically. Electrovolts. So that's that. Then the last one, which is basically 4.9 electrovolts. Beautiful. So these are all the energies that are possible when they transmit. I just want to observe if they're all different, because if they are different, that's great. 4.9, 4. Aha, there's a problem here. These two energies are the same. Now remember, wavelength is hc over your, energy of a photon. So basically, if you have all different energies, that means you have all different wavelengths. So you'll have different, basically, parts here. So you'll have a peak here, peak here. These are all going to be different. Each peak, basically, each peak is a different wavelength, pretty much. So if two of the stuff are the same energy, it means they will basically be on top of each other in the spectrum, basically. So this will be here and the other one will be on top of it, because they both basically have the same wavelength. If they have the same energy, they have to have the same wavelength. So basically we consider that as just one peak. We don't consider it as two. So that's going to be basically, we consider those two as one. So that's going to be basically, so how many in total? 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 9 in total. So basically when you look at this, it's going to be 9 basically lines. So that's 3, 4, 5, 6, 7, 8, 9. It's only going to be 9 basically. And these basically just tell you the different wavelengths that exist. And yeah, just be careful. Don't put 10. Because then you're basically doing these, you're repeating these, which is wrong. So you put 9 as your answer. Yeah, I think it makes sense. Let's try question 20. I think this is the last one. So it's very long, but yeah, let's smash it. All right, question 20. Two physics students, Jerome and Priya, set out to investigate centripetal force. Figure 17 shows the experimental setup and the apparatus that the students use. In reality, the students find that the cord is not quite horizontal, but dips downward slightly due to the gravitational force acting on the rubber stopper. Their teacher explains that they can safely ignore this effect when collecting the experimental results. Beautiful. We've actually done this kind of experiment. I remember when I was in year 12. And we did I think it was an investigation task on it, and it was very nice and easy. So let's have a try at this. So we have the rubber stopper, strong cord, position marker, beautiful. Insulated grass, ignore friction between the cord and the tube. Jerome and Priya note the following data in their logbook. So the radius of the circle is 0.75, okay. The mass of each metal washer is 30 grams, and their initial number of washers are 10. Basically, Priya holds the glass tube and sets the rubber stopper rotating in a horizontal circle. She maintains a constant radius of the circle by keeping the position marker at the fixed position just below the bottom of the glass tube. Beautiful. Jerome uses a stopwatch to measure the time for 20 revolutions of the rubber stopper, repeating this measurement 3 times. He notes all of the data collected in their logbook. The experimental is then repeated 4 more times with 2 extra metal washers added before each new trial is undertaken. Why did the students take repeated time measurements during the experiment? What a beautiful question. If you do any science in VCE, that is, chemistry, psychology, biology, you'll get questions like these. These are basically your analysis questions or your investigation questions. When we repeat a measurement, basically when we repeat the measurement a lot of times, what we do is we get different values and we basically average them out. And so when we average them out, we are decreasing the chance of random error. That's what we do. Basically, when you're repeating an experiment, there's many other stuff you can say, but I think the most kind of common kind of stuff that we use is when you repeat an experiment, you just basically decrease the chance of random error. So let's just say 1 mark. So decrease random error. Beautiful. The tension in the cord supplies the centripetal force that the rubber stopper needs to rotate in a circle. What is the cause of this tension? Beautiful. So let's have a look at this here. Basically, imagine doing this in real life. So basically, when you're rotating this and you're keeping a constant radius, so this is, not moving, basically. These two are not moving. You're just basically rotating and they're not moving. Of course, you're going to have a tension here that's going to be towards the center. Remember, your tension force is basically your centripetal force. It's that tension force because it's towards the circle. And so what's supplying this tension force is your force of gravity of the metal washers. If you basically, let's say, let go, like you don't rotate anymore, and you basically just, what's going to happen is basically this is going to go down straight away, fall. Because these metal washers, your force of gravity basically is going to basically push it down. So you need to basically have a velocity, of course. You need to be kind of rotating it at, of course, right angle to its force, your centripetal force. You're basically rotating at a speed where the tension force exists, and these two are going to be the same value, because if they aren't, if your force of gravity is bigger, it's going to fall. Basically, it's going to go down, and this is going to go down with it. So for this to be maintained, so for this to be like a nice maintained radius or a circle, these two have to be basically the same. And this is the thing that's causing this tension is your force of gravity. These metal washers are basically, imagine doing this in real life. So you're basically rotating, and you would feel that, imagine not even having an insulated glass, but when you're like rotating something, and you would feel like if you have something like a mass at the bottom, you feel like you're basically pushing down on it, and that's what's creating its tension. So yeah, I hope that makes sense. I mean, it's kind of a question that, it makes sense when you're trying to do it in real life. Yeah, like imagine just basically put a rope on a bucket and basically just kind of rotate it around your head. You will feel your hand, they'll be going up, but your hand's actually pushing it down because you're trying to equate that force, that tension force of that bucket with this force of gravity, so they don't fall off. And so basically that's what it is. Beautiful. So the thing that causes this force of gravity is your tension force is your force of gravity of washers. Beautiful. The gravitational force acting on the metal washer is given by mg. So mg is basically your mass times gravity, which is your force, where m is the total mass of the washers and g is the gravitational field. So symbol represents, so pi, constant, m, rubber of the mass of the rubber stopper, r is the radius of rotation, and t is the period of time. Develop an equation between mg and the quantities listed in table 1. Like what we just said. We said that the tension force is going to be equal to your force of gravity. Now, your force of gravity is that mg. And your tension force is basically your centripetal force. So I'm just looking at my formula sheet, because I have all these formulas in my formula sheet. So your centripetal force, because we want to write it in terms of pi, mass, r, and t, I do have one that. So I have 4 pi squared rm. R is going to be now big, because that's what we're using here. Rm over t squared. So that's another way I have that written here. And yeah, those are in terms of all those quantities. Now, because it's 3 marks, I think that's not going to get you full marks. So I had that already in my formula sheet, because this is another formula if you have all those quantities. So what I'm going to do is we have to prove it. So okay, let's prove that. So if we're saying that the force of gravity, so let's think about this. If I'm saying that the force of gravity, which is mg, is equal to your tension force, which is your centripetal force, which you can write as mv squared over r. We know that velocity, looking at my formula, so velocity can be written as 2 pi r over t. Because velocity is getting squared, if you're squaring this, you're squaring this whole thing, which basically means that this is going to be 4 pi squared r squared over t squared. And so what you're doing is you're multiplying by this m. So you're going to put a mass here. And you're also basically dividing it by r. So r will be at the bottom. So these will cancel out basically. And so you're left with the same formula. Absolutely, you're left with the same formula. And that's how you prove it. So beautiful. I'm going to rub this off. I'm just going to give that formula there. But I hope that makes sense how you kind of would want it. It's easily, you can easily get it. All right. Jerome and Priya record some of their results in table 2. The students are told by the teacher that they can use G equals 10 newtons per kilogram for their calculations. Fill in the blank columns in table 2. So we have the total mass of washers, M, and the gravitational force acting on the washers, which is mg. So let's do that. So basically 0.3 times 10. So that's 3. Okay, makes sense. So that's going to be 3.0. This here has to be then 3.6. This has to be 4.2. Just by looking at these, so that's going to have to be 4.8. And the other one has to be 5.4. Beautiful. So we have also the average times for the 20 rotations. So basically, we have that, and we want to calculate the period. Be careful. Period is the time it takes for one full rotation, not 20 rotations. So you basically have to divide all these by 20 to get the period. So 14 divided by 20, this is 0.70. The next one's 12.8, so 12.8 divided by 20, 0.64. 11.8 divided by 20, 0.59. Basically, 11 divided by 20, 0.55. 10.4 divided by 20, which is 0.52. And so we have our period, and we just have to do 1 over t squared. So 1 over our period squared. So let's do that. So 1 over, first one, 0.7 squared. We get basically 2.04. 1 over 0.64 squared, which is 2.44. The next one is 0.59. 2.87. So 55. 3.31. And then 52, which is 7. Why am I making two same figures? I should just make it to all of them 1, yeah. So I'm just going to rub all these out. So that's going to be 9, basically. It's going to be 4. You can write that as 2, basically. That's it. Just all in 2 significant figures. So let's double check something. So 1 over 0.7 squared. Yeah, perfect. Works. All good. Done. Using your values in table 2, plot a graph of the mg, or force, on the y-axis against the 1 over t squared on the x-axis on the grid provided below on your graph. Draw a straight line of best fit through the plotted lines. Include uncertainty bars in the x direction only, so plus or negative 0.1. Uncertainty bars in the y direction are not required, so 4 marks. Beautiful. Let's do the force first. So we're already given, okay, beautiful. So let's do the force. So the forces go by 3, 3.6, 4.2. The max is 5. And so there's, if I do 1, 2, it's going to be 4. So I'll do half of it. So basically this will be here, will be 2. So I'll start with 2, 4, 6, 8, yeah. 2, see it'll be 4. That's 6. That's be 8, basically. And your period 1 over 2 squared goes by 2, and it goes max is 3.7. So basically we can go by ones, yeah. So ones. So we can say that's 1, 2, 3, 4. Beautiful. And let's now plot those points. So the first one is, let's try it. 2. So basically 2 is where? Which is here. Oops. That's 2 right there. So 2, and it's going to be 3 on it. So 1, so 2, 4, 6, 8, 10. So 3 is over here, basically. Let me rub that out. Done. That's that point. 2.4 now. So 1, 2, 3, 4. So 4 is here. And so 3.6. So 3.6. All right. So that's 2. So 2, 4, 6, 8, 10. So that's 3. 3.2, 3.4, 3.6 is over here. Was it 3.6? Just want to double check. Yes, it is. Beautiful. Next point. 2.9. So 2.9 is basically here. That's 2.9 and 4.2. So it's going to be 4.2. So there it is, right over there. .2. 3.3. 3.3 is where? 3.3 is 1, 2, 3 over here. So 3.3 is going to be 4.8. 4.8 is going to be, so 2, 4, 6, 8, right over there. We're nearly done. Wow, this is so long. 3.7. So 3.7 is going to be 1, 2, 3, 4, 5, 6, 7 over here. And it's going to be 5.4. So that's going to be 2, 4, 6, 8, 10. Right over here, basically. Is that right? So it was 1, 2, 3, so 2, 4, 6, 8, 10. So that's 5 here. 2, 4. Yep, beautiful. If I was at 5.4. Yes, it is. So basically there. We can rub all these out, and now we can draw our uncertainty bars. So let's do that. So our uncertainty are only in the x direction. They're basically 0.1. All right, so if I have here a point, let's say, I always like to do this. If I have a point, basically each go by 0.01 on either side. So it's going to look like these, basically. This is your uncertainty. I'm going to just basically duplicate them on my iPad and put them on those points. So that's that point. Duplicate. That's that point. That's that point. That's that point. And I'm going to take the last one and I'm going to put it right over it. Oops. There we go. So we've kind of put them in those places. And those look perfect. Done. So I'm going to draw basically a line of best fit in the color orange. There to there. Done. Okay. Beautiful. Did we miss anything? Draw a straight line. Draw uncertainty bars. Beautiful. Everything looks good. This is the last part. Let's do it. So calculate the gradient of the graph plotted in part E. Alright, beautiful. So we know gradient. We just need 2 points on the graph that look nice. Having a look at this, which are 2 points that are nicely put? This one looks great, actually. I'm going to take that point, because it nicely passes through that line. And it's going to go here. It's the y value. Another point that nicely passes, having a look. Alright, I mean, we can take that one. That looks good too. So I'm going to take that one too. Looks also good, so. Perfect. So now, let's use our points. So your value here is 4.2, 4.4. So that's 4.4. We can say 4.4 minus 4. I'm just using the gradient formula, so y2 minus y1. And then 3 minus, basically 3 minus, so that's 1, 2, 3, 4, 5, 6, 7, 2.7 basically. And so that gives me what? What's the gradient of that? 4.4 minus 4, 3 minus 2.7. That gives me 1.33 approximately. So that gives me 1.33 as my gradient. That looks good. I mean, 1.33 in what units? I think they haven't given the units, so let's find the units too. So basically, it's newtons over your 1 over t squared, your period squared. And so that's the same as Newton's t squared, which is basically, t is basically second squared. Newton's second squared. That's the unit. Beautiful. I think they want the units because it's empty here. All right, next question. Using the gradient calculated in part F, show that the mass m, show that the mass of the rubber stopper is approximately 50 grams. Let's do that. Beautiful. So we said the gradient was what? Was mg over 1 over t squared. So it's mg over 1 over t squared, which is basically the same as mg t squared. And that's your gradient. That's what our gradient we calculated. And so we knew from that formula, going back to that formula, so it was mg. Look at my formula. What was our formula? Oh, 4 pi squared, was it? 4 pi squared rm over t squared. How do I try to look at this? If I multiply both sides of this formula by t squared, I get rid of this t squared here, and I actually get it over here. This here is the same as here. It means that our gradient, basically, I can actually rub this out. It means our gradient, so let me write that here. Our gradient, m, is equal to this value over here. So our gradient is 1.33, 4 pi squared, your radius of the circle as well. We were given, yep, so 0.75. 0.75, and the mass is what we're trying to calculate. So basically your m is 1.33 all over 4 pi squared, 0.75. That's going to give me, so 4 pi squared times 0.75. That gives me approximately, so 0.045 basically kilograms, which is approximately, times it by 10 to the power of 3, 45 grams, which is approximately 50 grams, to kind of round it up. So 50 grams, basically. So approximately that value there. Yeah, use the gradient and show that the mass of a rock is approximately 50. Yeah, so, I mean, I'll do this first, so, which is approximately 45 grams. It's approximately 50 grams. And that's it. Beautiful. I hope you guys enjoyed this video and learned something through it. Please make sure to like and subscribe. And yeah, I hope you have a great day and make sure you take care of yourselves. Bye-bye.